Okay, so in this sheet, we are looking at the ELECTRE method, which we also covered in the Python video. We want to see how it looks like in Excel. So let me quickly go through the method and see what we are doing here. So as I mentioned, for the ELECTRE, uh, the method doesn't gives us the ranking and doesn't specify the top choice all the time. So basically, it gives us the top choices. So it end up so it leaves us with top choices among like a set of choices that we have. So among like a couple of alternatives, it calculates and gives us the top uh, two or three or four top choices. And then when it happens, then basically we will need to apply another MCDM method on top of that to find the best one. But sometimes, because of the circumstances existing within the alternatives and their attributes, we might end up having only one uh, top choice from the ELECTRE method. In that case, we can say, okay, so we have the final answer. We don't really need uh, to go and do another MCDM approach. So the idea here is that it gives us uh, top choices that are fit in that kernel. And this kernel can be defined by two rules that we have here. So these are the alternatives that satisfy those two rules. And basically this is going to be our top choices. And in order to find those, we have to do some calculations. Basically, we need to find the concordance and discordance uh, of each combination of alternatives. And then after that, we have to find the concordance index and also discordant index. And from that, after finding those values, we need to compare them uh, with against threshold, which here we have the mean value. So basically this is the mean. This guy is the mean of all the C's here, and this guy is the mean of the D. Uh, these and then after doing that, we create this table. So this is the comparison table. So we are saying that if C PQ, for example, if C1 is bigger than the threshold, put yes. And the question here is that is D 1, 2 is less than threshold, yes. And if we get two yeses, the final answer would be yes. And this means that alternative A is better than alternative 2. Alternative 1, sorry, is better than alternative 2. So we really need to have yes. And for us to get yes at the last column, we need two yeses for the previous questions. So one yes and one no gives us no. So let's see how we can implement that in Excel. So this is, again, that housing problem. And these are the vector normalized value multiplied by weight. So we need to have the weighted normalized value, right? And we create the concordance column. And you see that, let me show you that as well. This is the concordance, and for concordance, basically what it says is uh, alternative 1, for example, for this guy, it says alternative 1 is better than alternative 2 in attribute 2. And this is the complement of concordance. So basically it tells us uh, alternative 1 is worse than alternative 2 in attributes 1 and 3, and so on. So after we create this, we just need to use this equation, this one and this one, to create this to find and calculate the values for C and D. So for example, for C, it's just a summation of the weights of those attributes. So for example, for this guy, we just sum up the weights of attribute 1 and attribute 3. And we also have this equation for D as well. It's a bit more complex than C, but anyway, we calculate this, and then let me show you how we did that in Excel. So the first we created the C and D columns, and then we find the attributes the way that I mentioned. And the next column here is that just a summation of the weights of these attributes. So basically for this one, we go and sum the weights of attribute 3, 4, 5, 6, and 7. So 3, 4, 5, 6, and 7. So it's going to be these weights. And if I look at this, it gives us this. Yeah. And for D, basically we are using this big calculation here, and we are basically, this is representing this equation here, so this absolute values, and then this is the minuses and the summation that we have there. Okay, so after we created that, we use these two columns and add the if statements. And the logic behind these if statements is exactly the same as what we had in that table. These two columns of the table is C is bigger than C average, or if D is less than D average. And we put 1 if we get yes, if this is true, and we get 0 if this is not true. So basically 1 means yes in that table and 0 means no. And then whenever we get 2 yeses, it means that we have the final yes as well. So in order to find the final column values, we just need to find the product of these two columns, right? These two columns, and finally we go and find the columns, the rows that gives us 1 in this column. So this column is basically this, right? So it's saying whether a alternative P is better than alternative Q. So for example, here we got 1 here, and this is related to C1, 2. It means that alternative 1 is better than alternative 2. So using this yeses here, we can go and create that one method actually is to create this diagram, and from this we can create this kernel. But what happened here is that if you look at this part of the table, we see that we got a bunch of yeses for attribute alternative 6, and basically it says alternative 6 is better than 1, 2, 3, 4, 5, and 7. Basically it means that this alternative, this house 6, is better than all of these. And so when we get something like this, then we don't really need to do any further calculations. We know the answer. The answer is that the house 6 is the best option for us. And one thing also for this if statement, so I didn't mention this. So this is if L3, for example, so this guy is bigger than L45. What is L45? L45 is the average, C average. Remember that we have that threshold, this threshold here. And if you look at this table, so basically we want to see if that each specific C is bigger than that threshold or that C average. So that's what happened here. So we already, after calculating this column, we went and calculated the average of that column. So you see that we did the same for column D as well, the column that has the values of D. So again, ELECTRE is quite time consuming to solve in Excel. I wouldn't recommend that if you are doing if you are calculating the ELECTRE method in exam, but still it's quite straightforward if you know the logic behind it. Building this type of table wouldn't be so hard. Okay, so what is Maximin? Another method to find the optimal solution is Maximin and Maximax. Let me show you, or maybe I search it in your book. Okay, so I want to start with Maximin. Okay. So for Maximin, what it does is that the overall performance of an alternative is determined by its weakest or poorest attribute. So let's say we have this table and we have alternatives, we have attributes, and they are all at the same scale. So basically it's a score from a 10-point scale. Uh, so that 1 is the worst and 10 is the best. And because all of them has the same scale, we don't need to do the normalization, right? They are in the same scale. Normalization doesn't really help us here. But the idea behind the Maximin and Maximax is that the data should be normalized. I mean, they have to be in the same scale. Otherwise, it doesn't work. So these are in the same scale. We can create this matrix. And for each alternative, we go and find the weakest attribute. So for A1, the weakest attribute is the minimum value. So this guy, this 2, is the minimum or the weakest attribute. So we just put it there. It's 2. So for A2, it's gonna be 2 again, 2 here, A3, 3, and so on. So after we did that for all the alternatives, we go in that column that we created and we find the max. So it means that among the poorest or weakest attributes, uh, alternative 4 has the highest attribute, has highest score, highest value of that attribute. So somehow it means that A4 has the best, weakest attribute, and based on that, we can select that as our optimal method. Maximax has the same logic, but instead of finding the minimum, we find the maximum. Instead of finding the weakest attribute, we are going to find the strongest attribute. And for that, for example, for A7, the strongest attribute would be 6 here. Put it there. For this guy, it's going to be 9, and so on. And at the end, we compare these values and find the maximum. And this is the alternative with the maximum value. And this is going to be our optimal choice. So in the Excel, honestly, it doesn't really have any kind of calculations here. So this is our data set for houses. We normalize it, as I mentioned, we need the normalized value. We use a linear normalization, and then we go and find a minimum because we want to do the Maximin, right? This is the Maximin. We find the minimum of each row. So this is the weakest attribute of alternative 1 and so on. And after we do that, within this column we find the maximum value, which is this guy, and then we can say that house 6 again is our best choice or optimal choice. Okay, so the next is entropy. The entropy is a weighting method. So whenever we do not have the weights specified for attributes, there's different ways to define those. One of them is entropy method. For the entropy, it has 3 steps. So the first step is, or maybe first step for us. So it has 3 main steps, but before doing that, we have to transform the cost attributes to benefit attributes, right? We want to all of these to be green, not red, right? Remember that these guys were red, right? These were cost attributes. So we took the inverse values here. So we have now all the values are all the attributes are benefits attributes, and then the first step here is to normalize. For the entropy, the normalization is dividing the value by the summation of each column. So if you look at the function here, just we divide each value by the summation of that corresponding column. And then after we do that, step 2 is to find the entropy, compute the entropy. So we have this minus h, and h can be calculated from 1 over ln of m, and m is the number of alternatives. So here in our case, the number of alternatives are 7. So it's going to be ln of 7, and then this is the product of each value and the ln of each of that value. So if I look at this, for example, so this is entropy, right? This is this equation. So we have the minus sign here, and this is the minus sign, and this guy here, ln7, is that h, what we have here. And then this is the product of each value, and it's ln, and as you can see, this is basically this equation here. And then if when we calculate this, the next step would be computing the weight vector using the entropy values. So we just put the entropy in this equation, and we get the corresponding weight. So for example, for this guy, we go 1 minus the entropy, and then here we have the summation of 1 minus entropies, as you can see here. And so now this is the weights. This row represents the weights of each attribute. So for example, this is the weight for distance to hospital, and let me see which one gets the highest weight. So yeah, this guy here, distance to school, gets the highest weight. Alright, and the last thing I wanted to mention is the Eigenvector method for finding the weights. Let me show you here in your textbook. Oh, it was there. Okay, so the way that we do this is to we give score to our attribute. So for example, here we have 3 attributes. We give the scores from 1 to 3 because we have 3 attributes. So here, for example, 2 is given a score of 3, the highest score, and then x3 is given a score of 2, and 1 is given the score of 1. And the logic behind this is that we want to create this matrix, and the way it works is that we ask the question that's how much alternative 1 is more important than alternative 2. And the way to calculate that is just use the score that we defined in the previous step. So x1 has the score of 1, x2 has the score of 3, so it's going to be 1 over 3. And this scoring is defined based on the decision maker. So decision maker has to decide what will be the scores. So how much x2 is more important than x1 for him, and so on. And similarly here, it's the comparison between x1 and x3, so 1 over 2, because the score of alternative 1 is 1 and alternative 3 is 2, and so on. So after we create this matrix, and for the diagonal, what we have is just alternative 1 over alternative 1, which gives us 1 over 1 which is 1. So that's why we got 1 here. And then we calculate the geometric mean of each row for this matrix. So we go and calculate the product of the values for the row, and to the power of 1 over the count, which is 3. So we have 3 items here. And we do the same for the second and third rows, and after that we calculate the sum of these final values, and then we go this over this, this over this, and this over this, and put it there, and this gives us the weight. So this is the weight column basically. So we have done this here exactly. So let's say a decision maker gives us this scoring to each of these attributes, and then using these attributes we can create, using these scores we can create that matrix that we were talking about. So this is the matrix that we were looking at. And so you see this one value, and then basically this is the score of 1 uh, over a score of 2, so you can see, and so on. So once we calculated this, then we calculate the geometric mean of each row. So it's just product of all of these values to the power of 1 over the count. So we have 7, it's going to be 1 over 7 here. We do that for all the rows and all the rows here, and then we calculate the sum, and then next we do this over this, and then we get the weight. So this is the weight, the final weight that we can use for calculations. And then the rest would be the weighted product method that I will leave it to you. I would say I would definitely prefer the Python code, and I would suggest that you do the same. Use the Python code for the weighted product method, weighted sum method, ELECTRE, and TOPSIS. But feel free to go over the weighted sum method and weighted product method. These are the most simple approach that we have in the textbook, so I will leave it to you. But please let me know if you have any questions. Please send me an email if you have any questions, so we can go over it together. And I guess that's it. Thank you.